Okay, ladies and gentlemen, this is Unit 4, Lesson 3, Building Quadratic Functions from Geometric Patterns. So we're going to start off here with looking at quadratic expressions and area. So figure A is a large square, figure B is a large square with a square, a 1 by 1 square removed, and figure C is two large squares with a 1 by 1 square added. So what we're asked to do is figure out the expressions for the area of A, B, and C if the side lengths were 4. So if the side lengths were 4 here, if this is 4 by 4, we could write this in two ways. 4 times 4, and I'm going to write that as 4 to the second power, or 4 squared, and then we could simplify that and say that that is in fact 16. So we're going to write that as 4 squared, or that equals 16, would be my area, so 16 units. Again, for B, if we are 4 by 4 here, again, this is 4 squared, but now I need to remove that 1 by 1 square, so it's 4 squared minus 1, which gives us 15 square units. And then simplifying this out, figure C, I would have 4 squared, and add on the 1. So if I did that, 4 squared plus 4 squared plus 1, 16 plus 16 plus 1 gives us 33. So now, if I remove an actual number and put in a variable, so what if this were x by x? So multiplying x times x gives us x squared. So with a variable, it would be x to the second power, and I can't actually put a number in there because I don't know what x is until you tell me a number. Same thing here. The blue area would be x squared, but I need to remove the 1. So this would be x squared and then minus 1. And then lastly, we would have x squared and x squared. And I'm going to simplify this and write it out up here. So we would have x squared plus 1. Now, I'm going to make some of my math visible. So this is 1x squared plus 1x squared. And then what we're going to do is combine our like terms. X squared and x squared are like terms because they're the same variable to the same power. So 1 plus 1 would give me 2x squared, and then I would bring on that constant of 1. So this would be 2x squared plus 1 in most simplest form. If we had 4x and 4x were the two side lengths, what I would do here is go 4 times 4, which is 16, and then x times x gives me 16x squared. So that would be, the area would be 16x squared. And then if I wanted to write that as 4x times 4x, but with an exponent, we could write that as 4x in parentheses squared. And then here for the area of part B, we could write this in a couple different ways. Oh, and I'm sorry, I actually made a mistake there. Let me go back. The first one here, it's going to be 4x squared, which is 16x squared. And then for B, it's going to be 16x squared, but I minus the 1. And then here we have 16x squared and 16x squared. So I have 16x squared plus 16x squared, and then plus a 1. In making my math visible, I see that x squared and x squared are like terms. They're the same variable to the same power. So I add the coefficients, 16 and 16, and I get 32x squared, and then I add the 1. So this will be 32x squared, and then plus 1. And now we're going to go and take it to another level of abstraction. So what if I have x plus 3 times x plus 3? So I could, for sure, write that as parentheses x plus 3 times x plus 3. And then I could write that with an exponent and put in parentheses x plus 3 and then squared. What we're going to do is stay consistent and keep this in the blue area as x plus 3 in parentheses squared. And then from that, I'm going to subtract off 1. So in here, x plus 3 parentheses squared, and then minus 1. And then lastly, this becomes x plus 3, another x plus 3 squared, and then plus 1. Writing that out, we have x plus 3 squared plus another in parentheses x plus 3 squared plus 1. Simplifying this becomes a little bit more difficult. So I'm going to show my math and make it visible. I have 1 and 1. And then I have x plus 3 squared plus another x plus 3 squared. So if I add 1 and 1, it would be 2 parentheses x plus 3 squared and then plus 1. So again, 2 parentheses x plus 3 squared and then plus 1. Okay, so now we're on the lesson 3.2 or part 3.2 of this, and we see expanding squares. So in looking at this, we're asked if step 1 has, we see 5 squares, and then step 2, I have 4 and another 4 has 8 squares, and step 3, I see a 3 by 3, which is 9 plus 4 more. That's going to give me a total of 13 squares. We're asked to describe step 5 and step 18. So in looking at this, I know that this is going to be quadratic because I see square patterns. And then I also see square patterns plus 4 along the outside. And then in looking at the pattern, step 2 helps me see the square better. I see step 2 as 2 squared plus 4 on the outside. And then I see step 3 as 3 squared plus 4 on the outside. Working back for step 1, that's 1 squared plus 4 on the outside. So if we had step 5 and then also step 18, step 5, we would have a 5 by 5 square to describe it and 4 along the outside. So in answering part B for step 5, I know that we would have 5 squared in the middle plus 4, and that would be 25 plus 4, which equals 29. Working out further for step 18, we would have 18 squared plus 4. I can't do 18 squared in my head. Some people can. Good job. In turning that up, using my calculator to do that, it's 18 squared gives me 324 plus 4, which is 329. So we see here in this part, step 5 has 29 squares, and step 18 has 329 squares. Now, if we had to write an equation to represent the relationship between the step number n and the number of squares y. First, before I do that, I like to write my variables. Here is my step number. And I need to use n. Now my step number is my input or my independent variable, or I'm going to put IV. And then my other variable, number of squares, that's my y variable, which is my output or my dependent variable. So to write that equation, the total number of squares, in looking at my number pattern, I take whatever the step number is, square it, and then add 4. So if my step number is n, I start with n, square it, and then add 4. Okay, ladies and gents, here I notice in step 1, the base is 1 and the height is 3 of my rectangle. In step 2, the base is 2 and the height is 4. In step 3, the base is 3 and the height is 5. I'm already noticing a pattern. For the step numbers, we're just going 1, 2, 3, 4, and then the height is going 3, 4, and 5. So for step 4, if I were to draw this, I know that the base is 4. And then in looking at the pattern here, 3, 4, 5, the height would be 1 more, which would be 6. So in drawing that, we would see it would be 4 by 6. So we sketch the next step in the pattern. Now, Kieran says that the pattern is growing linearly because the step number goes up by 1 and the number of columns also goes up by 1. So we see 1 by 3 and 2 by 4 and 3 by 5 and 4 by 6. Well, the relationship is not between the step number and the number of columns. So I can see where he's saying for sure the height of the columns is a linear increase, but if we figured out the total area, like this is 1 by 3, which gives us 3. 2 by 4 gives us 8. And 3 by 5 gives us 15 total squares. And 4 by 6 gives us 24. As we examine the increase from 3 to 8, I increase 5. And from 8 to 15, I increase by 7. We can see the increase is not constant. So on here, the pattern is not linear. The rate of change, or the increase, is not constant. And then to represent the number of squares after n steps, Diego wrote the equation. So here's Diego's. And then f of n equals n times n plus 2. And Jada wrote f of n equals n squared plus 2n. And then we have to say, is either of them correct? How do you know? So if we plug in a couple step numbers, like I'm going to plug in step 2. So at step 2, we know n is 2. So using Diego's equation, f of 2 gives me 2 times in parentheses 2 plus 2. 2 plus 2 first would be 4. So that is 2 times 4, which gives us 8. So f of 2 is 8. Using Jada's equation, f of 2 equals 2 squared plus 2 times 2. Simplifying that, 2 squared is 4, and 2 times 2 is 4. 4 plus 4 gives me 8. So we see here that f of 2 for all of these, or for both equations, is 8. So it's quite possible both equations are working here. So what I want to do now is look at, can I prove that n times, in parentheses, n plus 2 is equivalent to n squared plus 2n. So I'm going to go over here and show that work. So if I start with n times n plus 2, and I distribute n times n gives us n squared, and then n times 2, we would write 2n. We see that those two equations are the same. So actually, both students are correct.